Welcome to the first lecture in this series. Today we are going to take a look at number systems. So we'll start with the decimal number system as we lay a foundation for the binary number system. So this is what we are going to look at: learning outcomes, an introduction to the number systems. Then we'll dwell on the decimal number system for this lecture, and then we'll take a summary of everything. So by the end of this lecture, you should be able to define a positional numeration system. You should be able to describe the decimal number system, perform decimal arithmetic operations, that is addition, subtraction, multiplication, and division. Now, most computer electronic components are bistable in nature, which means that at any given time, they can be in one of the two states, that is on or off, or clockwise magnetized and counterclockwise magnetized. Now, these two states are usually denoted by 0 and 1, where 0, that's for off or false, and 1 is for on or true. Now, 0 and 1 are symbols of the binary number system. A unit of information in a computer is represented by a sequence of these binary digits. Binary digits is there, that's bits for short. Right? So bits is short for binary digits. Most computers use binary numbers even in calculations, which is called binary arithmetic, which we'll look at in the second lecture in this series. Both the binary and decimal number systems are examples of positional numeration systems. Any such system, in other words, any positional numeration system, requires only a finite number of symbols, which are called digits of that number system, to represent arbitrarily large numbers. The number of bits, which we are going to represent by B in that system, is called its base or radix. Right? So the number of bits, the number of digits in that number system is called its base or radix. So what it means is, in the decimal number system, the number of digits will be 10, meaning the base for the decimal number system is 10, or the radix for the decimal number system is 10. Any number can be represented as a sum of powers of the base B, where each power is weighted by one of the digits in the number. We will first look at the decimal number system before dwelling on the binary number system. Now, what is a decimal number system? This is a number system that has 10 digits used to denote the symbols. That is, it has the digits 0, 1, 2, 3 through 9, which represent the integers 0 through 9 respectively. Since there are 10 digits in the decimal number system, therefore its base B is equal to 10. Any positive integer n represented in the decimal system, represented in the decimal system as a string of decimal digits, may also be expressed as a sum of powers of 10, with each power weighted by a digit. For instance, let's suppose we have the number 103. This number can be expressed as a sum of powers of 10, where we are raising each of these numbers here to the power of 10, and then we multiply it by the digit that we have here. So what we are basically going to do is, we are going to multiply 1 by 10 to the power of something, and then we add 0 times 10 to the power of something, and then 3 times 10 to the power of something. Now, how do we determine to which power are we supposed to raise our 10? We start from the right, starting with the first number after the decimal point. In this case, we have no decimal point. So starting from 3, we are going to raise 3. We are going to multiply 3 times 10 to the power of 0. Then we move one step to the left. We are going to multiply 0 times 10 to the power of 1. We go one step to the left again. We are going to multiply 1 times 10 to the power of 2. Right. So this becomes 103 is therefore equal to 1 times 10 squared plus 0 times 10 to the power of 1 plus 3 times 10 to the power of 0. take note that 10 to the power of 0 is 1 and 10 to the power of 1 is 10. So this can be written as 1 times 100 plus 10 plus 0 times 10 plus 3 times 1. Likewise, 21 can be expressed as 2 times 10 to the power of 1 plus 1 times 10 to the power of 0, which is equal to 2 times 10 plus 1 times 1. Now, these two notations that we have here as equivalences of 103 and 21 are also called the expanded notation for these given integers here. So what it means is, let's suppose we had the digit right. Let's suppose we had the digit let me say 41. If we were to express, or maybe let me say 4110, if we were to express this in its expanded notation, we're going to say how many digits do we have here before the comma? We have 1, 2, 3, 4 digits. So that means our highest power is going to be 3. So we would say this is equal to 4 times 10 to the power of 3. Unfortunately, there is no power here. 10 to the power of, let me just say 10 to the power of 3 plus 1 times 10 to the power of 2 plus 1 times 10 to the power of 1 plus 0 times 10 to the power of 0. All right. We can go on to simplify this one, which means this will be the same as saying 4 times 10 to the power of 3, that's 1000, plus 1 times 10 to the power of 2, that's 100, plus 1 times 10 to the power of 1, that's 10, plus 0 times 1, that will give us 0. Of course, you can say 0 times 1, but that will give us a 0. All right. So that's how you do the conversion, or that's how you express them in their expanded notation. All right. So moving on, we observe that 103 is equal to 100 plus 0 plus 3. Thus, the digit 3 represents 3 ones, the 0 represents 0 tens, and 1 represents 1 100ths. So any fractional value in a decimal number system can be expressed as a negative power of 10. Right? So 10 to the power of minus 1 is equivalent to 1 over 10. In other words, what you are basically saying is, given a negative power, like in this case we have 10, let me just say 10 to the power of minus 1, this will be equal to 1 over 10 to the power of 1, right? Now, 10 to the power of 1 will give you 1, so this will be the same as 1 over 10. I mean, 10 to the power of 1 will give you 10, so this will be the same as saying 1 over 10. Right? So whenever you have a negative index, you just say 1 over that number raised to the positive index. That's how you do it. Which means when we have 10 to the power of minus 2, this will be the same as saying 1 over 10 to the power of 2, which is 1 over 100. 10 to the power of minus 3, that will be equal to 1 over 10 to the power of 3, which is 1 over 1000, etc. Right. Now, for instance, let's suppose we have a number 50.34, which is expressed, that number is expressed in its expanded notation as follows. Right. Starting from this dot, going to the right, we are going to raise our base to the power of 0, 1, 2, 3, 4, etc. Starting from this decimal point, going to the left, to the right, I mean, we are going to raise our indices starting from minus 1, minus 2, minus 3, etc. Right. So as we have seen in on the previous slide, 50 is the same as saying 5 times 10 to the power of 1 plus 0 times 10 to the power of 0. Then plus 3 times 10 to the power of minus 1 plus 4 times 10 to the power of minus 2. That's how you would express this number in its expanded notation, or in its expanded form. But the number of digits to the right of the decimal point is called decimal places. So in this case, we have 1, 2 digits to the right of the decimal point. So that means this number has 2 decimal places. We can add numbers in the decimal point, or in the decimal number system. Right. So what is important is when we are adding our numbers, make sure that you align the decimal points vertically. Right. So like in this case, we have 34.23 plus 10.023 plus 1 plus 11.5. Right. So we need to align our decimal points. If you write 34.23 and then 10.023 and then 11.5, you would realize that these numbers, they have different numbers of decimal points, or decimal numbers. I mean, they have different numbers of decimal numbers. So or decimal places. So what you need to do is, for these others, like this one, which just says 23, and this one is 023, and this one is 0.5, you add additional zeros to the right of these numbers so that they all have the same number of decimal places. Adding these ones, 0 plus 3 plus 0, that's 3, 3 plus 2 plus 0, that's 5, 2 plus 0, 2 plus 0 plus 5, 2 plus 0 plus 5, that's 7, 4 plus 0 plus 1, that's 5, 3 plus 1 plus 1, that's 5. So this will give you 55.753. Right? So note the inclusion of additional zeros to ensure that all numbers have the same number of decimal places. And those zeros are added to the right. You cannot add the zeros to the left or anywhere in between those numbers. Likewise, we can also subtract decimal numbers. For us to be able to subtract the decimal numbers, we also have to vertically align the decimal points. So in this case, we have 35.5 minus 20.002. So we need to align the decimal points. 35.500 minus 20.002. Subtracting these two will give you 15.98. Then we can also multiply decimal number systems. Now, when it comes to multiplication, the alignment of decimal places, I mean the alignment of decimal points, does not matter. What matters is the number of decimal places that you are supposed to have in your final answer. All right. So here we want to multiply 2.35 times 43.162. For us to do that, we can say 43.162 times 2.35, right? To simplify the multiplication, we can start by multiplying this first number by 2. So to do that, we'll put zeros first, 0 for 5, 0 for 3, and then we start multiplying. 2 times 2 will give us 4. 2 times 6 will give us 12, which is 2 carry 1. 2 times 1, that's 2 plus 1, that would be 3. 2 times 3, that's 6. 2 times 8 times 4, that's 8. Now we have only multiplied by 2. We are left with multiplying by 3 and by 5. So we now want to multiply by 3, and we are going to put a 0 first for this 5. Then we'll say 3 times 2, that will be 6. 3 times 6, that's 18, that's 8 carry 1. 3 times 1, that's 3 plus 1, that will be 4. 3 times 3, that's 9. 3 times 4, that's 12. Now we are multiplying by 5, which is our last digit here. We'll say 5 times 2, that's 10, which is 0 carry 1. 5 times 6, that's 30 plus 1, that will be 31, so that's 1 carry 3. 5 times 1, that's 5 plus 3, that will be 8. 5 times 3, that's 15, which is 5 carry 1. 5 times 4, that's 20 plus 1, that's 21. We now add these three numbers, this one, and this one, and we get 101,430.70. Now, we now need to determine where are we supposed to insert our decimal point. So to determine where we are supposed to put our decimal point, we come here, we count how many number of decimal places do we have in both of these numbers. So here we have 1, 2, 3 decimal places. Here we have 1, 2 decimal places. 3 plus 2 will give us 5, which means this answer of ours must have 5 decimal places. So we'll have 1, 2, 3, 4, 5, and then we put our point here, or our decimal place here, which makes it 101.43070. We can also multiply decimal numbers, and to do the multiplication, we can also divide, and to do the division, always make sure that the divisor is an integer. Always make sure that the divisor doesn't have a decimal point, right? And then you can go on to do the multiplication. So for instance, let's suppose we want to divide 387.167 by 2.55. 2.55 in this case is our divisor. So we have to make sure that 2.55 does not have a decimal point. In other words, we have to move this decimal point 2 places to the right so that it becomes 255. And once we move the decimal point 2 places to the right, we have to do the same again on our numerator. All right, we have to do the same again on our numerator or on our dividend. So we have to move the decimal point 2 places to the right again so that it becomes 38716.7, like we have here. All right. Then we go on to do the division. That's a long division. We say 255 into 3, it doesn't get in there. 255 into 38 doesn't get in there. 255 into 387, it gets in there one time. So we are going to write our 1 on top of this 7, right? So we will now say 1 times 255, we get 255. We subtract 387 minus 255, we get 132. Now 255 does not get into 132, so we bring down 1 here. It becomes 1,321. How many times does 255 get into 1321? That's 5 times. 5 times 255 will give us 1275. We subtract 1321 minus 1275, we'll get 46. Now, after getting 46, we bring down 6 so that it becomes 466. And then how many times does 255 get into 466? That's 1. So we multiply 1 by 255, we get 255. We subtract 466 minus 255, we get 211. We bring down 7. All right. Now we can see that here, when we are now bringing down this 7, it's now after the decimal point. So we can align our decimal points here. We have our dot, and then 255 into 2117, it will get 8 times. We multiply 8 times 255, we get 2040. Subtracting 2117 minus 2040 will give us 77. And then we bring down this 0, we get 770. How many times does 255 get into 770? That's 3 times. If we multiply this 3 by 255, we'll get 765. Subtracting 765 from 770, we'll get 5. All right. Now we can end here where we are now saying the remainder is 5. But if you want to go on, you would then say how many times does 255 get into 5? That will be 0, and then you add a 0 to 5 so that it becomes 50. But then, yeah, let's just end here. 151.83 remainder 5. We can go on and on dividing that one. So we have seen that most electronic computer components are bistable in nature, and we have seen that both the binary and decimal number systems are examples of positional numeration systems, meaning that they require a finite number of symbols or digits. In this lecture, we covered the decimal number system and its associated arithmetic. In the next lecture, we are going to look at the binary number system, where we are going to dwell on for some time.